Okay, this is the last section of Physics 1 B for November 30th. And what we're going to talk about for the rest of class is interference, superposition, and standing waves. So interference is the idea that if you have one or more waves at the same position that collide with each other, let's say you have two waves on water that are moving towards each other, or you have two waves on a string that are moving towards each other, then you can get what's called an interference effect. So I think for me, the simplest way to understand this is to imagine a string. So we've got some kind of a string. And then within that string, we have a pulse traveling on the string. So say a piece of the string is traveling with a pulse. And let's use a really simple pulse that's like a square pulse, like this. So I've got a pulse that's traveling to the right like this. And let's say it has an amplitude that we call A. And over on the right, we have another pulse that's traveling in the opposite direction. So another pulse that's traveling in the opposite direction is coming right here. And let's say that this pulse, just to keep things really simple, also has an amplitude that we call A. If this pulse is traveling in this direction, then what happens when the two pulses collide with each other, let's say somewhere right in the middle right here, is you're going to get a pulse that has basically double the amplitude when they collide with each other. And the interesting thing is, I don't know if I made that big enough, but when they pass through each other, so when the two waves are at the same location, then they interfere with each other. And we call this type of interference constructive interference. Constructive because it's constructing a larger wave. And the opposite is destructive interference. I'll show an example of that. And one thing that's really cool that happens after they collide with each other. So I want you to think about what would happen. If this was like two billiard balls and they collide with each other, what happens after they collide? You don't get anything like this. You don't get any kind of interference. But two billiard balls, if they were moving towards each other, after the collision, what would happen to them? And if I have a ball that's traveling this way and I have a ball that's traveling this way and they hit each other, if they have the same mass, what happens after they collide?
Wouldn't they kind of like go through each other?
The balls?
Oh, the balls? Oh no. They bounce.
They bounce off. But the waves, you're right. The waves do actually go through each other. That's what's interesting here. So these two waves, what would happen is they would after they collide, they maintain their exact same amplitude. And this is a medium that has no kind of loss to it. There's no dampening, but anyway. The two waves, after they collide with each other, they just kind of pass right through each other. Whereas physical objects bounce off of each other. So waves they're kind of funny like that, right? Now, what's the opposite example of this? So the opposite example, which is called destructive interference, is when I have a wave that's traveling here, and I have another wave that's traveling that's kind of down. So you kind of have you'd say like a crest and a trough, or a maximum and a minimum. And if these two are traveling like this, and again, they have the same amplitude A, when they meet each other, what happens is they totally cancel each other out. And we call that, when the two waves add together in the middle, we call that destructive interference. And again, after they pass through each other, now it's going to be like, oops. You're going to have your waves like this now. They've kind of inverted positions, and this one's traveling this way, and this one's traveling this way. So constructive and destructive. Your book has, arguably a much better picture of this. Right here. Right here. And then we can also observe this. Here we can put these. Up here. Yeah, so this is your book's version of this. You've got your constructive over here on the right, The two waves get close to each other. They start to add together at this point. They add together maximally at this point, and then they pass through. And then here we have these two waves. They come together. They cancel out right in the middle, and then they pass through each other again. We can see this happen on this one if we do this. Gotta put damping in here. This thing just will keep going forever. So we can see this happen here because when the wave reaches the end, it bounces back, right? So what we can do is you can send a second pulse, and then those pulses will basically start to interact with each other. Now in this case, let's lower the damping a little bit. So we can send a pulse, then we can send another pulse. See how they kind of like, they interact with each other? Let's reset. If we go no damping, this will be kind of extreme, because then you do a first pulse, second pulse. And now, look at that. It's so weird watching how they interact. It's nothing like particles. It's nothing like billiard balls. It's something completely different, right? I think, are we seeing, it's only showing us one type, right? Which type of interference are we seeing here? Is this destructive or constructive?
Destructive.
It's destructive, right? Because every time the two waves hit each other, they're exactly, what you would say they're exactly like the opposite phase. One is up and one is down, right? All right, let's see if we can, let's see if I can make it so we have them constructively interfere. So what I'm gonna do is like that. Oh wait, there's only one way to do this, I think. No, what I could, let's see what we can do. We'll go up this one, and we'll go down with this one. That should work. Ah, there's too much damping. Let's turn the damping off. So up, and then down. There's still, oh, because every time I reset it, I get damping. So we'll go up, and then down. I think I've got multiple waves going here. But I think this is working, right? So right when they hit right here, see they double in size? That's constructive. And then when they hit over here, it's also constructive. Because these two waves are only meeting when they are at the same phase. They're both at their maximums, or both at their minimums. So we call that destructive. This is constructive. This is constructive interference. But I love the fact that the waveforms never disappear, you know? The initial waveform that we produced over here, because there's no energy loss in the system, the damping is 0. Yeah, those same waveforms, they stay together. It's just so, it's almost kind of eerie to me watching this. Of course, the moment you introduce any damping at all, they will eventually damp out to 0. And that's what a real wave would do. Real waves can't go on forever. Okay. Yeah, there we go. All right, so we call that interference. And interference can happen in all kinds of ways. There's interference of sound waves that can occur. There's interference of water waves, waves on strings that we're seeing here. There's also interference of light waves. And it's, what if the waves are parallel? How can we make them parallel, Tom? What do you mean? Good question. I just want to... Perpendicular. Okay, so one wave would travel this way, but then the other wave would come this way. One wave would be basically traveling kind of in the positive y direction, and one wave would be traveling in the x direction. That'd be interesting to think about. Let's, so I think what I say next will answer your question to some extent. That's kind of a complicated question, though, actually. All right, so in order to understand what happens when these waves hit each other, we use what's called the principle of superposition. This is something that comes up all the time in physics. So if I have two waves that interact with each other, and I want to find the waveform that's produced when they hit each other, the waveform we would write, y of x and t, if I have one wave that's represented by y1 of x and t, and I have another wave that's represented by y2 of x and t, then you literally just, you sum those wave functions, and that'll give you the new wave, basically. Okay. Now, if they were perpendicular to each other, the part of the problem in describing that with the method we're trying to do here, Tom, is that if I have a wave that travels this way, that would be kind of a wave in the y direction, right? But if I want to make a wave that travels, I'll use if I want to have a wave that travels this way, we'd have to use x as a function of y and t. So you'd be adding kind of a y function and an x function. And yeah, I guess you'd use some kind of vectors. Cam's probably right. To figure out how they would interact with each other. There is, on this thing, this one allows us to have waves in multiple directions. But then how do those interact when...
I think maybe circular motion would kind of result in it.
Yeah, and that's kind of what these are doing, right? They're kind of traveling in... I don't know if we call it circular. This looks pretty...
I mean, it's like elliptic. Yeah.
Even elliptical is not going to cut it. It's going to be way more it's way more complicated than that. Look at that. Isn't that cool? All right, we're getting way beyond. We haven't even talked about this one yet before we understand what this one is. We want to understand this one first. Then we'll go back to that one. But it is possible you can have waves that interact perpendicularly in nature, though, right? Because you could have a water wave traveling across the pond in one direction. You could have another water wave travel across the pond in the other direction. And you should be able to describe how that would be working. Because both of them would be the height of the water interacting with each other. And that definitely happens where waves in the water cross each other in perpendicular directions. Okay, so that's our principle of superposition. And the last kind of topic that I need to introduce are kind of what are called boundary conditions. So for waves on strings, there's going to kind of be three possible boundary conditions. There's going to be waves where they're connected. The best way to describe boundary is just to use this thing. This really is a really good applet. So there's three possibilities up here at the top. There's a fixed end, a loose end, and no end. These are what we call boundary conditions, okay? If I'm producing a wave and it's oscillating like this, it's a lot easier to see if we just use the pulse. So what happens to that pulse whenever it hits the end over here? What do you notice happens to that pulse when it hits the end? And the same thing happens on both ends, by the way. What happens to the pulse?
It just flips.
It flips. It flips exactly by one phase. So this is a fixed end, and what we see is that the wave flips 180 degrees. So that's one boundary condition, okay? So a fixed end, what happens is that the fixed end, this is all about Newton's third law, right? For every force, there's an equal and opposite force. This thing tries to pull up, this thing pushes down. That's pretty much it. You get 180 degree phase inversion whenever it hits the end here. So if it was a maximum, it bounces off as a minimum. Maximum, minimum, minimum, maximum, maximum, minimum, minimum, maximum, and it just repeats. So the fixed boundary condition, what it does is it leads to 180 degree phase shift, which means basically max becomes a min. If it's open on the end, you no longer have an external force, and so what happens... Well, no end, it doesn't come back, right? If the end is loose, watch what happens now. Is there a phase inversion? Nope. It goes in as a maximum, or a minimum, comes out as a minimum. Goes in as a maximum, comes out as a maximum. Goes in as a minimum, comes out as a minimum. This is no phase inversion. No phase inversion. There is a phase inversion on the left side because the left side's fixed, right? So you get the flip because of Newton's third law. The flip. But on this side, no flip. No phase inversion. All right. So if it's open on one end, that leads to no phase shift. And it just reflects backwards. One thing that's really interesting about this idea, if you could understand what's going on here, is that this same type of thing, it turns out, will happen really with any kind of a wave, basically. This same type of thing will happen really with any kind of a wave. And this phase inversion, due to boundary conditions, it also applies to light waves. And it turns out that when light bounces off of certain surfaces, there's a shift in the light. And one of the effects of this is well beyond the scope of this class. This is something you learn about about in physics. In physics 1D, but I just want to show a picture because I find it's really interesting to kind of give you a hint of as what's to come. Oily film. I think that's what I want to search for is oily film. Have you all ever seen this kind of thing? You look at an oil on the ground and there's like all of these colors, right? Mm-hmm. Color of light is related to frequency of light or wavelength. And it turns out that this effect that happens right here is it's exactly the same as what's going on here. A really strange thing occurs where when light bounces off the top surface of the oil, now think about it, oil is a film, right? So there's thickness to it. There's non-uniform thickness, actually. But it turns out that light will bounce off the top of the film, and it will bounce off the bottom of the film as well. And those two things will interfere with each other. And depending on the thickness of the film, you get different colors. So this same effect of, where is it? Oh, of what happens at these boundaries happens in that picture, and it leads to this. So when you get to 1D, just I'm sure your teacher will bring this up again because it's just the natural thing we compare it to. Because this we can see, right? Boom, it flipped. And you just have to trust me that when you get to 1D, the same thing's happening here, which I think is pretty amazing, honestly. That these features of waves that we learn about, they apply to all waves. Light waves, sound waves, everything. They apply to all of them. And so understanding how these waves work is definitely really, really helpful. Boundary conditions. So fixed, 180 degree phase shift, open, no phase shift, right? Okay. So let's take this idea and look at standing waves. A standing wave is going to be what happens when you get a perfect kind of connection between the incoming wave and the outgoing wave so that you kind of produce a standing or fixed waveform. Okay, so here, let's start off with this picture. Those are standing waves. These are standing waves. This is a huge picture. This picture, I can barely fit it on the screen. These are what are called standing waves. All right? These are called standing waves. They have certain features. They have nodes and antinodes. The nodes are these points right here, here, and here. Or on this string, it's here, 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 and here. The ends will always represent standing wave. Or sorry, the end points will always be nodes. What's happening here is that you have a string that's being oscillated back and forth at the front right here by some type of vibrator. Maybe the vibrator's on this side, actually. Can't really tell, but it doesn't matter. Both of these points at the ends are fixed points that basically don't move very much. So a node is a point that basically kind of stays stationary. And the wave itself is going to be that the string is going to oscillate back and forth like this. And to see how this might be produced, again, we go back to this guy right here. And what we can do is, if we put a little bit of damping on here and go to oscillate, pretty sure it'll probably set up some kind of a standing wave. So why does this happen? This is not a perfect standing wave, okay? It's pretty close. I'm going to show you a better example. But that point right there is not moving very much, right? That point right there is not exactly moving very much. So this is pretty close to a standing wave. It's not exactly a standing wave. Why does it happen? So you have a wave that travels to the right? But then that same wave gets reflected off of the right end right here, and it travels back to the left. Except when it travels backwards, it's always going to be the opposite phase, right? We saw that you get this phase inversion that occurs, right? So a wave traveling forwards may look like this, and the wave traveling backwards may look like this. right? Because they invert phase on this point right here, and then they invert phase on this point right here. So you can get this perfect cancellation that occurs at each of the nodes. And that's what we call a standing wave. Now I'm going to show you a video for this. Okay, I watched this video. This is what we would do in the lab. It really is not very good. Look how unhappy this person looks. We're not going to watch that one because I watched it and they just don't do a very good job of producing it. So instead we're going to do this one. This one uses a machine. But standing waves, you can definitely produce these. Like if you get a jump rope and go with like one of your friends and hold it together, you can try for yourself that you can produce standing waves. It's really very, very easy to do. But this is a very good demo of standing waves here. I need to switch this so you can hear sound. Okay, applications. All right. It's 4 minutes, but I think it's worth watching. Tell me if you cannot hear the sound.
What we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to.
Or I can tell it at least.
What's up?
About the sound?
You can't hear it?
No.
Really? I'll try it again.
When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
I think that's really cool. That point right in the middle, it just stays there.
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle's a node. So we have 3 nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5.
The number there is frequency, if you didn't catch that. It's the frequency of the generator.
And there we go.
This is called the fundamental, or the first harmonic. There's actually extra motions in there, if you can tell.
It's basically the scenario of a jump rope. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was that around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, Let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth.
Do you notice how it, like, I'm just going to show this again so you can see it. Watch, like, these we call these modes. These are called modes. Watch how, like, like, as soon as he gets to the number, what you're looking at just, like, it like instantly changes, basically. Watch this.
The sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations.
There we go. So those are standing waves on strings. I don't know if you all find that fascinating, but the first time I ever saw someone do that demo, I was blown away. Like, I think this is something that, like, I think it makes logical sense that such a thing could exist. I mean, we've gone through the reasons why this happens. You have a wave coming this way and a wave coming back. But seeing how definitive it is as you get to these higher wavelengths, how clear it is that there's just this perfect waveform that occurs, and that, I think, kind of more importantly, that while it runs, I don't know, it feels like it's almost like magic in a way that the waveform itself doesn't ever get disrupted. These nodes are just perfect. Here, let me mute this. Yeah, these nodes are just completely perfectly still, you know? They're barely moving at all. They're barely moving at all. And it really shows that there's these kind of fundamental ways in which you can find these things. They're called modes because they're like these fixed modes for the strings. All right, let's change windows. And we can actually show each of these modes with another one of these FET demos here. And let's see, how do we do this? There we go. So we call these normal modes. This is the n equal to 1 mode, or the fundamental, the first harmonic. This is the second mode. You get exactly 1 fixed point here, and then nodes on the ends. And then this is 3. It turns out that you can get another type of a mode if you switch to this. This is the first mode in the longitudinal direction. That's the second mode in the longitudinal direction, where again, this point becomes a node. And then there's the third point, where now the nodes are actually somewhat in between here and here. You can also have situations where you have combinations of modes. Kind of that mode plus this mode. And it can get really crazy when you get 3 of them. All right. So let's look quickly at the math behind this. We're kind of running out of time. We have about 20 minutes left, so I might skip through some of these steps just to kind of get to the high points of this. Okay, so let's talk about how we form a standing wave mathematically. So let's say that you have the following functions that represent your wave. You've got y of x and t equal to, let's use a negative a cosine of kx plus omega t. Oops. Let's say that this represents an incident wave that's traveling left. And let's say we have another function, this is y1, another function y2, that represents a wave traveling in the opposite direction, and a wave that is exactly 180 degrees out of phase. So to make it travel to the right, we just put kx minus omega t. This is going to be our reflected wave. technically, they're both going to reflect, so which is incident and which is reflected is important. But the point is that they need to be 180 degrees out of phase, right? One has to flip, right? Then if I want to combine these two waves together using the superposition pencil, we say that y of x and t is going to be the superposition of y1 plus y2. And now that's going to look something like this. It's going to be a times negative cosine of kx plus omega t plus cosine of kx minus omega t. Now what we can do is we can combine these two things together. The way that we're going to combine them together would be to use the sum formula. Cosine of a plus or minus b is equal to the cosine of a cosine of b minus or plus the sine of a times the sine of b. And what will end up happening here is when you combine these two together, I'll leave the math to you if you want to do it. It's just a lot of algebra you got to work out here. A lot of terms are going to cancel, some are, some aren't. But what's going to happen is it's going to be the sine terms that are not going to cancel due to the nature of the fact that the sine of things that are negative can flip the sign, whereas that can't happen with cosine. So these terms will all cancel, these terms won't. And so what you'll get as a final result here is y of x and t ends up giving you 2 times a, so there's your double the amplitude that you might expect, multiplied by the sine of kx, and then the sine of omega t. And this is our standing wave function. We call it a standing wave again because it has fixed nodes. So at each instant, each time t that we choose, the shape of the wave is a sine curve, but the wave's shape stays in the same position, oscillating basically up and down. And to figure out where the nodes occur, the nodes are going to occur when the sine of k times x is equal to 0. Those are going to be the x coordinates of the nodes. The places where sine of kx is equal to 0 means that x has to be equal to, basically, if x was 0, you'd get 0. If x was like pi divided by k, you get 0 because sine of pi is 0. If x was like 2 pi divided by k, you'd also get 0. Or, since k is equal to 2 pi divided by the wavelength, these occur at values of x equal to... so you plug in 2 pi over lambda in here, so you're going to get 0, lambda over 2, lambda, 3 lambda over 2. Right? Okay. So we know something about the positions of the nodes that are going to occur. And the other thing that we can say about this is if we consider these waves that are oscillating up and down, then we have basically waves that look like this. We have waves that are fixed between 2 points that look like this. We call this one n equal to 1. We call this one n equal to 2. And what we can say about it is that if this is the length of my string, in the case of n equal to 2, the wavelength is equal to the length of the string. In the case of n equal to 1, half of the wavelength, lambda over 2, is equal to the length of the string. Hopefully you all can see that. This is a full wave. This is a half wave. Oh, sorry. Sorry. I'm being confusing. The 2's on the wrong side here. In this case, the wavelength is double. Oh, it's the same thing. I guess it doesn't matter where you put the 2, does it? Yeah, it's only half a wave. So, okay, however you want to think about it. They say the same thing. So, in general, what we can say is that the wavelength is going to be equal to 2 times L divided by N. That's our general expression for the wavelength, where N can only be equal to 1, 2, 3, etc. We call N equal to 1. This is called the fundamental. This is like kind of It's kind of a musical definition, because this is how waves on strings behave in music. N equal to 2 is called the second harmonic. It's also referred to sometimes as the first overtone, in case you see that language show up. And we can relate these wavelengths to the frequencies, because since we know that the velocity of the wave is equal to the frequency multiplied by the wavelength, that means that the frequency of the wave, if we plug in lambda into this equation over here, we would have v over f. So the frequency of the wave is going to be given by this expression, n times v over 2l, where the first frequency is just going to be equal to v over 2l. This would be we call this the fundamental frequency. This is the frequency that you produce when you pluck a string on a guitar. If you just openly pluck the string, this is going to be the fundamental frequency, or what's called the natural frequency, at which it's going to oscillate. All right. The second harmonic, F2, is basically equal to 2 times F1. This is something you saw in the video where he doubled the frequency and he got the second harmonic. Because again, it's n times v over 2l, but the F1 is this. So in general, what you can do is you can write that if I want to know what the nth frequency is, which is what we have right here, it's equal to n multiplied by the fundamental frequency. It's kind of a useful expression, but this is the more general one. And then finally, what we can do is connect this back to the velocity, because we said before that velocity of the wave on the string was equal to the square root of the tension divided by the mass density. So then we can tie this all together now to say that the nth frequency is equal to n times v over 2l. So I'll just write it as n over 2l times the square root of t over mu. And this connects everything back together again to say that the tighter your string, the bigger that the pitch is going to be, and the lower density for your string, the larger the pitch is going to be. So you can control the pitch that a string produces simply by manipulating the tension on a guitar. That's done by tightening the strings, and you can make higher sounds if the density of the string is thicker. So if you've ever seen a bass guitar is designed to play really, really low tones. And how does, maybe someone here can tell me, maybe some of you know, how does a bass guitar look different from a regular guitar? Anyone know? You want to either ever played one or just been to a music shop and noticed what the difference is? No, the strings are usually the same size, although they technically could be longer. What John says is right. It has 4 strings versus 6, and the strings are much thicker. They're way thicker. They're really... Let me see if we can find a bass guitar. I don't know that any of these images are going to do it justice, but maybe we can find one where we can kind of see. I can't really see there, can you? What if we just search for bass guitar strings? That one kind of does it justice, right? Like, you can see those are really thick. Especially this one. Like, that's a really beefy string. Whereas guitar strings, like, they can be really skinny, right? If you just go to, like, regular guitar strings. Here we go. They do get thicker on the edge because they have to, but you get these really, really, really skinny ones here as well. Anyway. So, there we go. I guess we have time to do at least one problem. Oops. Yeah, fundamental frequency, second harmonic, third harmonic. I don't know which one's better to do. Let's do this one. Okay, I'm going to go through this relatively quickly because I'd like to spend at least the last 5 minutes of class talking about next week, which we have next week is finals. So, okay, giant bass violin, or did it say violin or is it just viol? I don't know. In an attempt to get your name in the Guinness World Records, you build a bass viol, I guess that's a type of instrument, with strings of length 5 meters, that's really far, 5 meters is like gigantic, between fixed points. One string with a linear mass density of 40 grams per meter is tuned to 20 hertz fundamental frequency. Okay, so that tells us what the fundamental frequency is. Again, fundamental means n equal to 1, so f sub 1 is 20 hertz. A mass density is mu, so mu is 40 grams per meter, so that's going to be 40 times 10 to the negative 3 kilograms per meter. And the length of our string is 5 meters. We want to calculate A, the tension in the string, B, the frequency and wavelength of the string of the second harmonic, and then the frequency and wavelength of the string of the second overtone. Second overtone is third harmonic, just to keep things really complicated. Okay, to find tension, what we can do is we can use really any of the equations we want to. The easiest one to use would be this one. So F1 is 1 over 2L square root T over mu. Solve this for tension, so we'll get 2L F1 squared should be equal to T over mu. So then we multiply this by mu like this. So we'll get 40 times 10 to the negative 3 kilograms per meter, multiplied by 2 times the length, which is 5 meters, times the fundamental frequency, which is 20 hertz. We're going to square that. This is going to give us tension. We can check the units here. This is meters squared per second squared. It'll cancel out with one of the meters. We're going to get kilogram times meter divided by second squared, which is definitely units of force. So 10 times 20 is 200. Squared would be 4e4. This is 4e negative 2. $1,600. Did I do that right? I probably made a mistake. Can you all calculate that real quick? Oh, 320. I did something wrong. I don't know what I did. Wait. Oh. Wait, y'all got something similar. Let me try it again. 2 times 5 times 20. 2 times 40 e minus 3. Oh, it is 1,600. Okay.
Yeah.
Cool. All right, so that's our tension. That's part A. Okay, part B. We want to find the frequency and wavelength on the string for the second harmonic. There's two ways to do this. I think the simplest way to find the second one, so for n equal to 2, what we can do is we can say that F2 is equal to 2 times F1. So you just double it. So F1 is 20 hertz, so you do 20 hertz times 2. So it's going to be 40 hertz. And then, okay, I swear I'm... There we go. The wavelength on the string of the second harmonic. Okay, so lambda sub n, the equation that I had above, you do 2L divided by n. So 2L divided by 2. So this is actually just equal to 5 meters. That's what the wavelength of the second harmonic is. So it's the length of the string, right? To visualize that, if you want to. This is n equal to 2, where the wavelength is equal to the length of the string. That's the wavelength and the frequency. Part C, we want to find the frequency and wavelength of the second overtone. The second overtone is basically just n equal to 3. So f sub 3 is going to be 3 times the fundamental frequency. So that's going to be 60 hertz. And then lambda 3 is 2L divided by 3. So that's going to be 2 times 5 meters divided by 3. So this is 10 over 3, or 3.33 meters. These problems are... I think they're pretty easy. They can get really tricky. There's ways these questions can be asked that things get tricky, but I don't know. I think waves are pretty simple compared to a lot of stuff we've been doing this semester. I think heat engines much more complex than this. But yeah, that covers pretty much everything. There's 2 topics I didn't get to that I wanted to, which is the intensity of waves and then the decibel sound scale. You're more than welcome to read about that yourself. We also didn't quite get to sound waves. You can read about that yourself if you want to, but sound waves are not much different. And then I guess one other thing we didn't get to is how what's it called? Pipe instruments work. You can read about all this stuff if you want to in chapter 16. But fundamentally what's going on is standing waves. And, if you understand one type of standing wave, it should be pretty easy to understand another type. So, before we leave today, we have 4 more minutes. I just want to mention we do have a exam next week. November really just kind of got away from me. I had definitely intended on assigning for y'all another assignment from the lab manual, and then basing the final exam off of lab manual problems. For whatever reason, I just kept putting that off, and I never got around to it. So your final for this class is going to be very similar to your final from, to the midterm exam. I'm going to give a list of problems just like I did before. I'll share it on Canvas. I'll probably also share it in Discord in case you're having difficulty accessing Canvas, as I know sometimes it will go down. You'll have 1 problem to present to me. The expectation is you need to present it in as much detail as you possibly can. Ideally, I'd love it if you could find some way to share your screen and show me the steps as opposed to simply providing giving me the document in advance, because if you give me your work in advance, it's nice. We can go through it. But if you can find some way at all of sharing at least some of the steps with me, that would be good. Even if you don't end up sharing all the steps. But yeah, so we'll do that next week. We'll just end up having that 1B lab manual assignment. I'll try to grade it this week if I can. You'll have 1 more assignment in Mastering Physics that I'm going to post today. It'll be due next Friday. You'll have roughly 2 weeks to finish it, 12 days. And that's pretty much it. Yeah, as in working out the problem line. Look, I want to be 100% clear here. If there's no way that you can find to do that, it's okay. It's totally okay. If you don't feel comfortable doing that, it's also okay. I'm not going to dock you points. I didn't dock anyone points because I said it's totally acceptable if you work out the problem in advance and then you send me a message with your problem. That's fine. You email it to me, Discord message, whatever. That's totally fine. But I learn more about what you're explaining to me, and I'm also going to be somewhat, what's the word for it? I'm going to be a little harder on you if the problem's already worked out, because I will assume that you can get through the explanation of the problem relatively quickly. And so I'll have to kind of use questions to kind of probe and make sure you understand things. When you work it out step by step, what I'm going to do instead is probably help you. I don't know if that distinction makes sense. It's like if you're already going to give me a worked out problem, I'm just going to be kind of I'm going to poke you and be like, hey, what's this? How did you get this step, etc. Right? If you're explaining the problem line by line, then I'm going to be much more likely that if you make a mistake, I might be like, hey, are you sure that's right? Does that make sense? So it becomes more... I don't know how to describe that, but I guess I described it.
I understand that.
Okay. To put it simply, I'll be nicer to you if you do that. Nice is the wrong word. I just mean I'm going to be more helpful to you if you're working it out and you make a mistake. I'm going to be less... If you have it all worked out and there's mistakes in there, I'm going to be pretty hard on you, Now, that doesn't mean that you won't be able to get full credit. As long as I point out a mistake and you can tell me why it's wrong and you can fix it on the fly, it doesn't matter what form it came in. Everybody's going to have an equal shot at getting a good grade. I'm sure... So you can use... People have used video. I'll tell you what people have done. People have used video. Some people have used something like this. I will say one thing I do not want you to do because it ends up just not being very good. I don't even know if this will let me do this. do not... Okay, here, I'll let me show you how we can do this. Paint. We go to paint. I do not want to see stuff like this. Please don't do this kind of stuff. I can't read that. And no matter how hard you try, it will either take forever. Yeah, if this is all you can do, don't do this. Just send me a copy. So you have to have... Huh? What's up?
No, I missed paint.
Yeah. So you kind of have to have some kind of a stylus. Yeah, don't write with your mouse. If this is all you can do, just write it on a pencil and paper and then upload it. That's fine. I just would vastly prefer that you do things like what I just did, ideally. Now, again, if you don't have the technology to do this, that's totally fine. I'm just saying, for me, that's what I would prefer. Again, I'm not gonna dock you points for this at all. Okay, what other questions y'all have? We're over time, and I'm still recording because I want anybody that isn't here today to be able to hear all this stuff too. So please take the time to ask me whatever you want. And technically, office hours start now anyway. So. Angela will be the same as before. Your problems will be posted so Sunday morning or Saturday, but it'll be around 24 hours in advance. You'll have at least 24 hours. Good question. Any other questions? Look, everybody did great the first time around that we did this. I was very pleased. I don't think it's super challenging in and of itself because many of these problems are quite easy. I think everybody performed very well the first time around. Yes, Tom. So we'll do the same thing that if you're in the first half of the alphabet, you will be going on Monday. If you're in the second half of the alphabet, you'll be going on Wednesday. And just to reiterate, you can always hang around because some people go faster than others, and we'll probably get ahead. So, if you notice me just sitting in this channel and nobody's in here, I might be like last time. What I did was I just typed in the 1B chat and I said like, hey, by the way, if you're ready to go, you can join. So if you are sitting around, sometimes people don't show up on time. Sometimes people don't show up at all. So just be ready. Because if you want to get it done and get it out of the way, because I mean, personally, if this was me, I would want to go first. I'd want to be the very first person to go so that I could just get in there and get out and be gone. You know what I mean? And be done for the day. Because waiting around kind of isn't fun. Nonetheless, I'll still give you a rough time estimate of when you're going to go. But just be ready if you're willing to be flexible to just pop in and join the channel as you need. I don't think I'm going to be pulling too many problems from the first half of the course, but I might. Just if I don't really feel like some of the problems from the latter half of the course are worth asking. But most of the questions are going to come from the last few assignments. Mostly thermodynamics, because I think that's what really the second half of the course has mostly been about, is about thermo. And I will very likely include some of these problems if I find if I determine that they're worthy, the ones that I post up. But, yeah, if you did well the first time around, there's no reason to think you won't do well this time around. Hopefully no one feels too nervous about this exam. Hopefully it doesn't take up too much of your time. I'm sure you've got all kinds of projects and other exams you've got coming up as well. So I want this to be as painless as possible because, the whole COVID teaching online and learning online thing it's pretty limited. So don't want to make the end of the course any more stressful than it needs to be. I know taking exams is a very, very stressful experience, regardless of how well you know the material. Any other questions? Okay, I'm going to stop the recording here, but if you do come up with questions, I'm